Well, students, in the last video, we discussed about the refraction through a spherical surface. The spherical surface may be a convex or a concave spherical surface, and object is placed in rarer or object is placed in denser, and we got the relation between the object distance, image distance, and the radius of curvature of the spherical surface. In this video, first we will discuss about a lens or lenses. In this video, we will discuss about the lenses. So, what is this lenses? What is this lenses? Or what is a lens? A lens is a portion of a lens is a portion of transparent refracting medium. Some portion of a transparent refracting medium means refraction occurs through that medium. Transparent refracting medium, right? Bound by two surfaces. If some refractive medium is there, it should bound by two surfaces. At least one surface is spherical. A lens is a portion of a transparent refractive medium bound by two surfaces. At least one surface is spherical. At least one surface is spherical. If both the surfaces, if one of the surfaces, it is bounded with some refracting medium is there, both the surfaces, if you consider no surface is spherical, means you can say that is like a plain glass plate. We have derived an expression on that. That is your lateral shift. There we consider how the refraction occurs through a plain glass slab. But lens consists of some refracting material like your transparent refracting material like your glass. The lens we are using generally made of glass. That is the refracting material bounded by two surfaces. At least one of the surface should be spherical. So, commonly used, if this is the so, then the commonly used lenses are the commonly used spherical surfaces, or the commonly used lenses are convex lens. One is the convex lens and concave lens. Convex and concave lens. Then what is a convex lens? The convex lens is the lens whose middle portion is thicker and edge is thin. Middle portion is thicker and edges are thin. Concave lens, middle portion is thinner and edges are thick. Then that is okay. Convex lens, or this convex lens is also known as the convergent lens because it converges the rays. convergent lens. This is also called as a convergent lens. Similarly, concave lens is also called as a, this is also called as the divergent lens. This is also called divergent lens because it diverges. It is also called as a divergent lens because it diverges the rays incident parallel on the lens, so it will diverge the rays. Convex lens, if parallel rays incident on the lens, then it will convert the rays. That we will discuss later stage. But there are commonly convex lens and concave lens. And in the convex lens, the middle portion is thicker and edges are thin. In convex lens, in the one, there may be lenses are, the convex lenses may be of different types. One is double convex lens. Next, a double convex lens, or plano convex lens, or concavo convex lens. Let me show double convex lens. This is a double convex lens. Double convex lens. The middle portion is thicker. Edge. These edges are thinner. Both the surfaces are convex. Plano convex lens. One of the surface is plane. The other is convex. And it will read always. The surface will read first, whose radius of curvature is larger. For a plane, or a line, for a plane surface, its radius of curvature is at infinite. But for this convex lens, what is radius of curvature? It is the radius of that sphere. So this is a sphere. This portion is a part of a sphere. It has a radius, that is the radius of curvature. But for the plane surface, the radius of curvature is at infinite. So we will read like that. The radius of curvature which is larger, that will first read plano convex lens. Concavo convex lens. Concavo convex lens is like this. Middle portion is thicker. We will make this thick, right? We will make this thick. Then this will be thicker, like this. Okay. The middle portion is thick. Similarly, number 2, the concave may be of again 3 types. You can say one is double concave lens. Next, plano concave lens. Next, number 3 is the convexo concave lens. Convexo concave lens. Double concave lens. Both the surfaces are concave. Double concave. Middle portion is thick. Middle portion is thin. Edges are thick. Plano concave. And this surface is a plane. Plano concave. Convexo concave. Right? Middle portion is we will make the middle portion is thinner. Like this. Yeah. And you can make this like the middle portion is thin. So this is thin, these are thicker. So this is a convex concave. This is a convex. So convexo, this surface is convex, this is concave, convexo concave lens. So these are the different lenses. So the lens may be convex or concave. Convex may be of 3 types. Concave may be of 3 types. Okay. But the most commonly we will use this type of lens: double convex lens and double concave lens. Here, mostly we will use these lenses. Okay. Now, before I go to the lens, discuss about the lens part. Then next part we will discuss about some terms associated with the lens. One of the commonly used term for a spherical surface, for a spherical refracting surface, we are using a term called as the pore. Pore means it is the middle portion of the spherical surface. Similarly, in a lens, we generally use that term here, the middle portion we can say also, that is called as the optical center of a lens. Remember, that is very, very important. What is the optical center of a lens? That we will use here, optical center. This is a term, optical center of a, what is the optical center of a lens? That is commonly we use this optical center one. What is this optical center of a lens? Optical center, you can say, it is, for an optical center, is a point on the principal axis of a lens. Let me take a convex lens. This is the principal axis, we can say. A point on the principal axis, a point on the principal axis such that a ray of light passing through it, a ray of light passing through it was undeviated. A point on the principal axis such that a ray of light incident on it was undeviated. Right? So, optical center, a point on the principal axis, on the principal axis such that a ray of light passes through it was undeviated. Undeviated. This is one of the definition. Okay. So the ray incident, it goes undeviated. Okay. And another you can say that if in the same convex lens you can say. So similarly, this is also true for a concave. For this is convex. For a concave lens also you can say double concave. Really? So this is the principal axis. And this is the optical center. And a ray incident on that optical center, O, you can say, it goes undeviated. This is a ray incident, goes undeviated. Or you can say, it is a point lying on the principal axis of the lens so that a ray of light whose refracted path passes through that point, whose refracted ray, a point lies on the principal axis, a point lying on the principal axis, so that a point lying on the principal axis, so that a ray of light whose refracted ray passes through that point, refracted ray, suppose a ray is incident like this, it gets refracted. How it gets refracted? If it goes refracted means, suppose this is the incident ray, let this is an incident ray, the ray gets refracted, traveling from rarer to denser, bends toward the normal, and it will pass like this, the ray bends like this, let me draw like this, incident ray, and this is the refracted ray. So, the refracted ray passed through that point, the refracted ray passed through that point, the refracted ray passed through that point, will have its emergent path, like this is the emergent path. Now it is traveling from denser to rarer, bends away from the normal. The emergent path will parallel to the incident ray with the incident ray. So these two rays should be parallel. This is the actual incident ray, and this should be parallel. These two rays should be parallel like this. The actual incident path, you can show like that. If this is the actual incident path, if there is no refraction, if you show this is the actual incident path, and this will be the refracted ray or emergent ray, which will be parallel to this one, which will be parallel to this one. This is the actual path, actual incident path, and this is the emergent path, emergent ray, which should be parallel. So this point is called as the optical center. Okay. Again I am repeating. It is a point lying on the principal axis so that a ray of light whose refracted path, a ray of light whose refracted path pass through that point, will have its emergent path, parallel to the direction of the incident ray. Parallel to the direction of incident ray. Actual line of action of the incident ray. This is the emergent ray. So this is the optical center we will use here. The others are there. Other parts are there. But the principal axis also there is a definition. The principal axis is what? There are two surfaces, curved surface. One is this curved surface has a center of curvature. This curved surface has a center of curvature. This one has a center of curvature this side. This has a center of curvature this side. So the line joining the two center of curvatures, that is called as the principal axis. Similarly, this surface has a center of curvature. This surface has a center of curvature. The line joining the two center of curvature is the principal axis. Okay. So other definitions we will discuss later stage when we will discuss clearly about the lens formula. Right? That is the later stage we will discuss in the later. So this is a term generally we will use in our derivation of a relation. Now we discuss a long question. Generally this is a long question that we will derive. That is your Lens-Makers formula. Next is the Lens-Makers formula. Lens-Makers formula. What is Lens-Makers formula? When we are using this lens in our general uses, like in our when we go for an eye specialist, if we have a problem, he provides us the lenses of different focal length. So a lens is made such that it should be designed so that for different purposes the focal length should be different. We will discuss what is that focal length, what is that focus, but remember for the time being the focal length should be different. Means when you are using a lens, its focal length is different, means it has different purpose of use. So the lens should be so designed that the two refracting surfaces, means the two radius of curvatures, next the two radius of curvatures, and the refractive index of the medium, of the lens, that is so chosen that it should have different focal length for different purposes. Means a Lens-Maker formula, you can say Lens-Maker formula is a relation that connects focal length of a lens to it connects the relation between focal length of a lens. It relates the focal length of a lens to radii of curvature. There are two radius, so radii of curvatures. It connects the focal length of a lens, radii of curvatures of the spherical surfaces, and the refractive index of the material of the lens, That is the Lens-Maker formula. Means why it matters means by using that we will make or we will design a lens and it can be used for different purposes. Okay, so this is the lens maker formula. And as usual, the sign convention is same. When you are using this formula, sign convention is same. All the distances for lens in spherical surface, you are telling that all the distances should measure from pole. There is the term is called pole. Here the term is the optical center. So here all the distances should be measured from the optical center. Next, the distances measured along the direction of light incident are positive. Opposite to the direction of light incident are negative. The distances measured upward or transversely above the principal axis are positive. Below the principal axis are negative. That is the sign convention when we are using this lens maker formula. Next, another one is that while using this lens maker formula, the assumptions, here also we will use some assumptions. While using the refracting surface also, we are using some assumptions. Here also we use some assumptions. So what are the assumptions? Some assumptions. First assumption is that the lens is thin, so that the lens is thin. The lens is thin, so that the lens is thin, so that distances measured from the poles, distances measured from the poles, because there are two surfaces, spherical surfaces for a double convex or double concave. There are two spherical surfaces, so there will be two poles. So distances measured from the poles of the surfaces, the distances measured from the poles of the surfaces can be taken as equal to, can be taken as equal to the distance from the optical center. The distance from the optical center of the lens. Means the distance is measured from the pole to a point. Suppose object is there from one of the convex surface. Object is placed in front of a lens. There is a convex surface. Suppose you are measuring from one convex surface object distance from pole to object distance. That is same for a lens from pole to that point. They are same. Means they are very close. I will show that in the figure. Next, the number 2 is that the aperture of the lens is small. That is most important. Aperture. What is the aperture? Aperture of the lens is small. Means the aperture means what? It is the portion of the lens. It is the portion of the lens which is for light emergent or light incident on that refracting surface on which the light incident, the effective diameter, that is the aperture. The aperture of the lens is small, right? Then the next one is that the object should be a point object. The object should be a point object. The object should be a point object. We will not discuss for a extended object. We will discuss for a point object. And the range of light should be the range of light incident, refracted. The range of light incident, refracted are para-axial. The range of light, what are the range of light? Incident ray, refracted ray are para-axial. The range of light are para-axial means the range of light are para-axial means the incident ray, the refracted ray. Already have taken that. Para-axial means the incident ray, the refracted ray or the emergent ray from the lens. They make small angle with the principal axis. They make small angles with the principal axis. Clear? So with these assumptions, we will now derive the lens maker formula. With these assumptions, we will discuss the lens maker formula. Right? Now we discuss the lens maker formula. Now go for the ray diagram. And here I will discuss the lens maker formula for a convex lens, and for a concave lens you can derive. Both are. So I will derive, that is also similar to this one. I will discuss for convex lens or simply a double convex lens. I will derive the lens maker formula for a convex lens. And once I derive this convex lens, you know the derivation, then we will go for concave lens. Convex lens is a double convex lens. Okay, let me draw the ray diagram. So now I will how we draw this one. Now go for the ray diagram. So a lens. Now first I will draw the double convex lens. Let me draw here a double convex lens like this. Now I will take a double convex lens. That is very, very important. That is a double convex lens. For understanding purpose, I have taken this type of lens, but the lens should be in the assumption this is a very thin lens. This is a very thin lens, but for understanding, I have taken that. And this is the optical, a principal axis which passes through the optical center. This is the principal axis which passes the optical center. Let that optical center I will take as a C. See the optical center. And this is called as your aperture. This is the curve surface called as the aperture. Clear? Now, let us consider pole for this surface. This is a convex surface. It has a pole. Let me tell this is pole as a P1. For this surface, it has a pole. Let this surface as pole P2. These are the two poles, the middle poles. For this surface, there is a central curvature. For this surface, there is a central curvature. Let me name the names also. Let the lens as one is X P1Y, X P2Y. These are the two convex surfaces. For X P1Y, this convex surface. This is the spherical surface. Which type of convex surface? There is a central curvature. It has a pole and a radius of curvature. X P2Y, there is the central curvature on this side, and the pole is there and a radius of curvature. Now the next part is now we draw the ray diagram. Let us consider an object. O. O being an object placed at a distance from the pole, from this surface. Right? And remember the refractive index of this medium mu2, and this is your mu1, which is a rarer. This medium is a denser, and this is made out of glass. Its refractive index mu2. This is mu1, and this is also a medium. Suppose you can say mu1. Rarer, and this is the lens portion. Some refractive medium bounded by two convex surface, so it is a double convex lens. Let us consider an object O placed at a distance u from the pole P1 for the surface X P1Y. Remember, first I am deriving, assuming that this is a refraction through a convex surface with the object in the error, I derive the ray diagram like that. Imagine that this X P2Y is not there. This surface is not there. Now we draw the ray diagram. So for that, what I will do, my first thing is that let us consider a ray incident from the object. One incident along OP1, and it passed to the, what is this called? Optical center of the lens or pole of this surface. Optical center is not there. There is no lens. Only we are discussing for this surface while drawing that. So the ray will OP1 goes undeviated, and it will pass like this to the lens. Like this. It will go like this. Undeviated. Because a ray incident at pole, it goes on repeated. Another ray incident at the point A on the convex refracting surface XP1Y. Then it has a center of curvature. The surface is a center of curvature. So to draw the normal, what we generally do? We will do like this. We will draw the normal like this. Let me draw the normal. Let me draw the normal for the surface. Then the normal on the surface. Let this is the normal on the surface. Clear? This is the normal. If this is the normal on the surface, this is called as the normal drawn on XP1Y, this curved surface. This point should be called as the center of curvature, C1. For the surface XP1Y, a line passing through the center of curvature on this surface will make perpendicular to the surface. So this is the normal. Then this will be the incident angle, suppose I1. Now what happens? Imagine that this surface is not there. Imagine that this surface is not there. Which one? XP2Y is not there. XP2Y is not there. If XP2Y is not there, then what will be the rate? Suppose it is traveling from rare to denser, and this total is a denser medium. Imagine this surface is not there. Then the ray will bend like this. Denser to rarer bends toward the normal, so the ray will bend like this. The ray will bend like this toward the normal, like this. Is that? And this angle is called as your angle of refraction R1. Next, then it incident of this surface. Now imagine, so this is the ray. If this surface is not there, then the ray will travel like this. This will go like this, and it will meet at a point, suppose I1. Suppose it goes on maybe this surface is not there, so this is the path incident ray OA and OP1. OP1 goes unradiated. OA incident at the point A on the surface XP1Y. After refraction, it goes along like this, AB and I1 along this path. It goes along this path. These two refracted rays, OP1, OA, if this surface is not there, XP1, XP2Y is not there, these two rays will meet at this point where? I1. So we can say I1 is the image of the object O, then the refraction takes place on the surface XP1Y. But in the lens, this surface is also present. If this surface is also present, the refraction, now AB ray travel through this refracting medium, when it comes to this surface, this side, again the refraction takes place. So do that refraction. Again let me draw another normal on this point. The normal on this point means, let this is the normal. This is the normal on this point. B on the surface XP2Y, if this is the normal on the surface XP2Y, it will meet at the point C2, the center of curvature for this surface. C2 is the center of curvature for this surface. Which surface? XP2Y. So this is my C2. So the ray will meet at the point AB, meet at the point B on the surface XP2Y. What happens? Because of this surface, now the ray is traveling from denser to rarer. It bends. So now if this is the ray, then you can show the incident angle. Angle of incidence, I can show this angle of incidence as, and we show this angle of incidence, this angle. Angle of incidence, now this is suppose I1, here I will take the I2. So this is the incident angle. AB is an incident ray for the surface XP2Y, I2 is the angle of incidence, and after refraction, it travels. It is denser to rarer, travel away from the normal. It bends away from the normal. So this is the normal on this surface. It bends away from the normal like this, and it will meet at the point, suppose I. Then we can say what? Because of this lens, I is the final image of the object O. But for this surface, remember, for this surface xp1y, if this surface is not there, O is an object, I1 is the image. Because of the lens, I is the final image of the object. And another part, for this surface xp2y, if this surface is not there, if I see this ray from this side, I will find that this ray is coming from this side, from this medium, that is the denser medium. So there is nothing in the denser medium, but I can say that this ray is coming from this one. Because of this image, this ray is coming, I can say this is an object, I1 is an object for the surface xp2y. For refraction occur on the surface xp2y, I1 is a object. Which type of object? It is a virtual object. It is not real object. It is a virtual object, and I is the real image for the surface xp2y, because the rays actually intersected the principal axis. Clear? Now we go to the expressions, or sorry, angles are that. Let this angle object makes alpha. Then final image always we take beta. And I1, let me take this is another image, suppose I take this as beta 1. Clear? And C1, let this is gamma 1, central curve is gamma 1. Let this is gamma 2. Is a gamma 2. And this is I2, then this angle is your angle of refraction R2 for the surface xp2y. Clear? We will do it in two ways, in two steps. One, first the refraction I will consider for the curved surface xp1y. For that, O is an object. For this surface, C1 is the central curvature, and I1 is the image. Next step I will discuss for the refraction to the surface xp2y, where I1 is a virtual object, I1 is a virtual object, I is a real image with central curvature C2 and pole letter P2. And the radius of curvature for this surface xp1y is, suppose P1 to C1 is a radius of curvature for the surface R1, and P2 C2 is a R2, radius of curvature R2. That is the example. And P1 to O, let the distance is a, consider the distance is a U. This distance is a U, and in the assumption we have already taken, P1 to O is object distance, so we can say for the total length it is the distance from optical center C to O is object distance. C to I1, let me take as V1, because it is not the real image. It is not a real image for the lens. It is, you can say, a virtual object for the surface xp2y. So I will take this as an image V1, position image V1, and C to I1 is V1, C to I is a V. These are the assumptions. And P2 C2 is R2, P1 C1 is equal to R1, and these are the angles. Right? Now we step by step. Now we go to the refraction at the surface. Refraction at the surface. Refraction at the surface X P1Y. For this surface, O is an object and I1 is the image. So do the same. Refraction at curved surface, spherical refracting surface. For a convex surface, object in mirror, image formed in anywhere. Maybe here it is looks like, here what? Image formed looks like in the error, but for this surface is there, you can say the image is in the denser. Okay? And this is a real image for this surface. For the object, real object O. For the surface xp1y. So now in the triangle, do the same thing. In the triangle, OAC1, OAC1, external angle is what? I1 is equal to alpha plus gamma 1. Then in the triangle, this is I1 A C1. I1 A, this is the same line. I1 A C1. I1 A C1. This triangle. Gamma 1. Gamma 1 is equal to R1 plus beta 1. R1 plus beta 1. This is gamma. Gamma 1 equal to R1 plus beta 1. This implies R1 is equal to gamma 1 minus beta 1. So I got I1 and R1. Okay? I got the I1 and R1. Okay? Now, using Snell's law, sin I by sin R, angle of incidence, sin of angle of incidence to a sin of angle of refraction is equal to the refractive index of which medium? First medium mu1 absolute refractive index is the second of refractive index mu2. So this is mu2. The ray is traveling from mu1 to mu2. So we find refractive index of second with respect to first. Or I can write absolute refractive index of second by absolute refractive index of first. Then for small angles of I and R, same procedure. Sin I is equal to I, sin R is equal to R. So I can put this I by R is equal to mu2 by mu1, or I into mu1 is equal to R into mu2. Now you put here, what is your I into mu1? This is sin I, this is I1, R1. For this surface, angle of incidence is I1, angle of refraction is R1. So this is I1, R1. So sin I1 is equal to I1, sin R1 equal to R1. I1, R1, I1, R1. Clear? I made this for instance. So I1 means alpha plus gamma 1, into mu1 is equal to R1 gamma 1 minus beta 1 into mu2. Clear? Then we can take this gamma 1 common, gamma 1 into mu1 minus mu2 is equal to gamma 1 mu1 minus gamma 1 mu2. So gamma mu1 minus mu2, gamma 1 common is equal to, take this side, minus alpha mu1 minus beta mu2 right? So gamma 1, then in the, now find out this alpha beta and beta 1, alpha mu1 minus alpha mu1 minus beta 1 mu2. In the triangle, in the right angle triangle, draw a perpendicular from A on this one, let it meet at the point M1. From B, it meet at the point, so this P2, and it meet at the point M2. These are the perpendiculars. So in that triangle, OAM1, tan alpha is equal to AM1 by M1O. In the right angle triangle, I1AM1 tan beta 1 is equal to AM1 divided by M1 I1. So in the right angle triangle, AM1 C1 AM1 C1, or you can say C1 AM1 C1 AM1 10 C1 AM1 10 gamma 1 is equal to 10 gamma 1 is equal to AM1 divided by M1 C1 M1 C1. Okay. Now after getting this 10 alpha, 10 alpha, 10 beta 1 and 10 gamma 1, now we will put here. We got alpha, beta 1, gamma 1. So for small angles, the same assumption is there. For small angles of alpha, because they are paraxial rays, so for paraxial rays, for small angles of alpha, beta 1, alpha, beta 1, gamma 1, we have 10 alpha, which is equal to alpha is equal to AM1 by M1O. 10 beta is equal to beta, which is equal to beta 1. 10 beta 1, which is equal to beta 1, that equal to AM1 by M1 I1. 10 gamma 1, which is equal to this gamma 1 is equal to gamma 1, that equal to AM1 divided by M1 C1. Now after getting this alpha, beta and gamma 1, now I put here in this expression. So putting that in this expression, give a name on this expression. Now what I will get? Gamma 1 AM1 divided by M1 C1 into mu1 minus mu2 is equal to minus alpha minus AM1 divided by M1O into mu1 minus beta 1 AM1 divided by M1 I1 into mu2. Clear? So if I cancel this AM1, take common AM1 here, rest will get mu1 minus mu2 divided by M1 C1 is equal to mu1 by M1O minus, sorry, minus sign is there, minus mu1 by M1O minus mu2 by M1 I1. Clear? So that is the expression. Now after getting this expression, clear? Then I will go keep that expression here. I can write this expression in the side. What the final expression I got here? Let me write here. Mu1 minus mu2 divided by M1 C1 is equal to mu1 by M1O minus mu2 by M1 I1. Clear? Now this is the expression. From this expression, for small aperture, next assumption is that for small aperture of the curved surface, M1 is close to P1, because I am not considering for the lens, I am considering only for this surface X P1 Y. So for the small aperture, this M1 perpendicular is close to P1 because this surface that is very close for small aperture. So in place of M1, I will put this P1, then I will get mu1 minus mu2 divided by P1 C1 is equal to minus mu1 divided by P1 O minus mu2 divided by P1 I1. This is the expression. Keep that. Don't put any. What is P1 C1, P1 O, P1 I1. No need to put the values. What is U, B. We will not put that in the UV. Now next part. As I have already told that first I will consider for the refraction on this surface. Then I considering the refraction for the surface x, p1, y. O is the real object, I1 is the real image. Next part, then I go for the refraction on this surface x, p2, y. I1 is a virtual object for this surface and I is the real image for the surface. With that consideration, now I will go to the refraction at the surface x, p2, y. So keep that in your mind. This is the final expression. So I will put here, I will write here. What is that expression? P1 C1 minus mu1. This is P1O minus P1 I1. This is the expression. Keep that. Next, I will go to the refraction at the surface x P2y. For that case, now I will take I1 is the virtual object and I is the real image for the surface x P2y. Right? Now the same case is the in that triangle. So here we will take what? I will find for this surface in the triangle for this surface x P2y. In the triangle I1 in the triangle I1 B C2 I1 B C2. Take I1 B C2. What is that I1 B C2? This is I1 B C2 in this triangle I1 B C2. Which one is extra angle? In this triangle I1 B C2. I2 is the extra angle, so I can write I2 is equal to gamma 2 plus beta 1. Gamma 2 plus beta 1. So I got I2. In the triangle, next I B C2. I B C2. I B C2. What is the extra angle? R2. R2 is equal to gamma 2 plus beta. R2 is equal to gamma 2 plus beta. Okay? Then, after getting that, I want you to write all these things again. Using Snell's law, sin I 2 by sin R2, because the refraction on that surface x P2y, angle of incidence I2 R2, that equal to refractive index of which medium? The ray is traveling from incident angle is in the denser going to the rarer. So the refractive index of rarer with respect to denser, I can write this is equal to mu 1 divided by mu 2. Mu 1 divided by absolute refractive index of rarer, absolute refractive index of denser. For small angles of I2 and R2, no need to write all these things. I2 by R2 is equal to mu 1 by mu 2. Put that I2 mu 1 is equal to R2 mu 2. Okay? I2 mu 2 is equal to R2 mu 1. Here R2 mu 1. Put that I2 R2. So gamma 2 plus beta 1 into mu 2 is equal to R2 gamma 2 plus beta into mu 1. Now we take the gamma common. Gamma on one side. Gamma 2, take this gamma 2 common. Take this gamma 2 mu 2 this side. Gamma 2 of mu 1 minus mu 2. Gamma 2 of mu 1 minus mu 2 is equal to beta 1 mu 2. Take this beta mu 1 this side minus beta mu 1. Clear? Take the sign. Mu 2 mu 1 gamma 2 mu 1 minus mu 2. Take this gamma 2 common. Clear? Beta 1 mu 2 minus beta mu 1. Then Go for the gamma 2, beta 1, beta. Use the triangle, right angle triangle. Or you have drawn the perpendicular B M2 I1. In the triangle, right angle triangle, B M1, sorry, B M2 I1, B M2 I1, 10 B M2 I1, 10 beta 1 is near equal to beta for small angle. I am writing beta 1, that should be equal to 10 beta 1 is equal to what? BM1 BM2 divided by M2 I1. In the triangle BM2 I 10 beta for small angles, that is beta, which is equal to BM2 divided by M2 I. M2 I. In the triangle BM2 C2, BM2 C2, 10 gamma 2, 10 gamma 2, because I mean gamma 2 beta 1 beta, beta 1 beta gamma 2 is equal to gamma 2 for small angles, that is equal to BM2 divided by M2 C2, M2 C2. Now put that in this expression. If you put that in this expression, then we will get gamma 2 BM2 divided by M2 C2 mu 1 minus mu 2 is equal to beta 1 BM2 divided by M2 I1 beta 1 minus mu 2 minus, what is beta? BM2 divided by M2I into mu 1. Here, this is your beta 1 and this is your beta. Now take this BM2 common from here and cancel that. Mu 1 minus mu 2 by M2 C2 is equal to mu 2 divided by M2 I1 minus mu 1 M2. For small aperture of which surface? Small aperture of X P2Y. For small aperture, M2 is close to P2. So here M2 I will cancel that, replace that by P2. Replace P2 C2 is equal to mu 2 divided by P2 I1 minus mu 1 P2 I. Got it? So I got that two expressions. Let me keep that two expressions. Clear? The second one is here. Let me write here mu 1 minus mu 2 divided by P2 C2 is equal to mu 2 divided by P2 I1 minus mu 1 divided by P2 I. Got it? Now I got the two expressions which are right here in the side. Now keep that in the two expressions. Then after knowing the two expressions, now for thin lens, in the assumption we have taken for a thin lens, because this is the lens vector formula for a thin lens. For understanding, we have taken a thick lens, but it is a very thin lens. They are almost not curved, they almost, it appears like, when you see through a naked eye, it will appear like a plane surface. So for a thin lens, P1 and P2 are close to C, optical center of the lens. P1 and P2 all are C, means the distance as measured from P1 or P2 is same as that of measured from C. Here, for a thin lens, P1 and P2 are close to C. Now we replace P1, P2 by C. Then, now the expression I will write. Now go to the expressions. Mu1, look the right side. Mu1 minus mu2 divided by, it is P1, I will take C1. Minus is equal to minus mu1 CO minus mu2 divided by CI1. Next one, mu1 minus mu2 CC2 is equal to mu2 divided by CI1 minus mu1 divided by Ci. I got the two final expressions, right? Now we adding these two, adding the above equations, what I will get? Take this side, add LHS mu1 minus mu2 of 1 by CC1 plus 1 by CC2. 1 by CC1 plus 1 by CC2 is equal to right, minus mu1 CO minus mu2 CI1 plus mu2 CI1. So they will cancel. If you add these two, plus minus they can cancel. The rest is minus mu1 by Ci. Clear? After that, use the sign convention. That is the most important. Using sign convention. What? CC1 along the direction of light incident R1. CC2, because this is the radius of curvature. CC2 means P2 C2, radius of curvature for this surface, opposite. So I will take this as minus R. Clear? Next, CO, object distance, always minus U. C2O or P1O, both are same. CO is equal to minus U. CI, image, final image, CI or P2I or P1I, that is the final image, plus D along the direction. Now you put the sign convention here. The rest is the mu1 minus mu2 divided into mu1 minus mu2 into 1 by CC1, 1 by R1, then minus 1 by R2 is equal to, then this minus mu1 divided by CO minus U minus mu1 by CID. So I can write this as mu1 minus mu2 into 1 by R1 minus 1 by R2 is equal to mu1 by U minus mu1 by D. Clear? Or I can write mu1. Right, now I will get here 1 by R1. Take a minus and multiply both sides. Multiply, because for the last purpose, multiply minus sign on both sides. So that we will get a relation as per our requirement. Minus sign on both sides. Means you multiply this minus mu2 minus mu1 into 1 by R1 minus 1 by R2 is equal to minus mu1 by U plus mu1 by D. Or I can write this side. Take this mu1 common. 1 by D minus 1 by U is equal to mu2 minus mu1 into 1 by R1 minus 1 by R2. So it is for convenient. I have taken the minus sign negative. Okay. In the beginning also you can subtract one another, then you will get the direct expression. But 1 by G minus 1 by U is equal to mu2 minus mu1 divided by mu1 into 1 by R1 minus 1 by R2. Or I can write this is equal to 1 by V minus 1 by U is equal to mu 2 by mu 1. That is for refractive index of denser with respect to our rarer. This medium with respect to denser. Mu 2 by mu 1. Minus mu 1 by mu 1. That is 1 into 1 by R1 minus 1 by R2. Or simply you can write this as a, or you can write if this outside medium or the rarer medium is air medium, the rarer medium is air medium, then mu 1 is equal to 1. So if mu 1 is equal to 1, for rarer you can take the absolute refractive index. 1 by V minus 1 by is equal to mu minus 1. Absolute refractive index of what? Mu is the absolute refractive index of material of the lens. Mean the denser medium, the glass medium suppose, into 1 by R1 minus 1 by R2. This is the required formula. If the object at infinite, if the object is at infinite, the image form at focus, then B is equal to F. So if you put that 1 by F, 1 by infinity 0 is equal to mu minus 1 into 1 by R1 minus 1 by R2. Well, students, this is the required formula, that is the lens maker formula for a convex lens. And this is also true for a double concave lens. You will get the same relation. 1 by F equal to the focal length of the convex lens should be equal to the refractive index of the material of the lens and the radius of curvature. Depends on the radius of curvature of the two surfaces. This is also true for a double concave lens. You can do that, you can solve, you will get the same result. Okay, thank you.